10% is the minimum annual increase in value for a specific type of plastic toy, a figure that consistently outpaces the growth of both gold reserves and the traditional stock market. This investment potential belongs exclusively to Lego sets. Why do these small, interlocking plastic bricks manage to carry such remarkable financial value over decades? The answer lies not just in the brand, but in the mechanical heart of their industrial origin. It is visible how raw plastic granules are transformed into precise geometric shapes through a production process driven by extreme technical accuracy. But this is just the beginning. One can notice the camera glides along the automated assembly lines where thousands of units move with synchronized rhythm. At first glance, the manufacturing seems simple, yet the design philosophy demands that every single brick produced today must fit together perfectly with one manufactured 40 years ago. Why is this level of mechanical compatibility maintained with such industrial rigor? High-precision molding is the only way to ensure that the friction and clutch power of the bricks remain constant over generations. The process is only gaining momentum as the facility operates at a scale involving millions of parts per day. Massive silos feed raw acrylonitrile butadiene styrene into the injection molding machines at high speeds. The equipment gradually heats the material until it reaches a liquid state, ready for high-pressure injection into steel molds. Everything only gets more complicated when considering the tolerances involved, which are measured in micrometers to prevent any deviation in the final product. The molten plastic fills the cavities of the molds with a quiet hiss of hydraulic systems. It is visible how cooling channels within the steel plates regulate the temperature to prevent warping as the bricks solidify. This meticulous control ensures that the structural integrity of the plastic remains stable for the duration of its life. The material leaves the molding station, transitioning into a calm stage of sorting and packaging. From here, the transformation moves to the next phase of processing where automated sensors verify the dimensions of every batch. Thus, the bricks reach the standard ready for the further stage of global distribution. 7,500 pieces and an extraordinary level of detail define the physical presence of the most expensive set ever sold through official channels. Why does a collection of plastic elements command a price that far exceeds its raw material and production costs? It seems simple to calculate value based on the number of bricks or the weight of the box. But in reality, the market worth of these objects is firmly anchored in the psychological realms of collective memory and dedicated fandom. The economic engine of this industry is not driven by generic shapes. Sets that appreciate the most are almost always inextricably linked to massive cultural universes, specifically the franchises of Star Wars and Harry Potter. One can notice how adult-focused lines, such as modular buildings and the Creator Expert series, follow a similar trajectory of value increase. But this is just the beginning. The process of appreciation accelerates the moment a set is officially discontinued by the manufacturer. Scarcity then combines with nostalgia to push the market price higher with every passing year. It only looks obvious that a product would lose value once it is no longer new. In reality, the absence of retail supply creates a secondary market where demand remains fueled by emotional connection. Everything only gets more complicated when a set achieves the status of a global cultural icon. The Star Wars Ultimate Collector Series Millennium Falcon stands as the definitive example of this phenomenon. Buyers who acquire this massive assembly are not merely paying for a specific quantity of injection-molded ABS plastic. They are investing in the preserved history of the Star Wars saga itself. The equipment of the imagination, translated into thousands of interlocking parts, turns a physical object into a vessel for narrative preservation. It is visible how the market responds to these icons with consistent growth. The value of these objects persists because the emotional bond between the owner and the cultural story does not degrade. This transformation of a simple toy into a high-value asset concludes this phase of the analysis, opening the road to understanding the next level of collecting. 28 tons of raw plastic granulate arrive at the production facility in a single heavy transport vehicle. Why must the material be handled with such technical rigor from the very first second? The manufacturing journey begins with this massive volume of raw material, but without absolute purity, the final elements would never achieve the interlocking precision required to fit together across multiple generations. The plastic granulate is immediately blown into towering storage silos using high-pressure compressed air systems. One can notice how the material moves through the air lines with a steady, rhythmic flow. But this is just the beginning. At first glance, the storage process seems simple, but in reality, it serves as the critical buffer that feeds the entire automated infrastructure. The material of choice is virgin acrylonitrile butadiene styrene, an engineering-grade plastic specifically selected for its mechanical properties. This specific grade of plastic is known for its high structural strength, good elasticity, and a unique ability to resist shrinkage or deformation over many decades of use. The plastic arrives in the form of small rice-sized pellets that exhibit extremely high levels of chemical purity. Every single batch undergoes rigorous laboratory testing for moisture content, color consistency, and specific chemical behavior before it is granted approval to enter the production line. It is visible how sensors and technicians verify that the material meets the exact specifications required for high-end molding. The process is only gaining momentum. From the tall storage silos, the plastic granulate flows downward by gravity and vacuum pressure through a network of long, winding pipes that span the entire factory ceiling. The material moves continuously inside these pipelines at a steady velocity, traveling deep into the injection molding area located at the heart of the facility. The camera glides along these conduits where thousands of pellets pass every minute toward their destination. Everything only gets more complicated as the material reaches the molding stations. The raw plastic granules are fed directly into the injection molding machines where the transformation into a liquid state begins. From these purified pellets, the manufacturer initiates the color blending process using proprietary chemical formulas that have been standardized for several decades. The raw plastic is thoroughly mixed with concentrated pigments at this early stage to ensure the color is distributed with perfect uniformity throughout the entire material volume. 50 colors are currently produced by the facility, and this is not the limit. Each specific hue is tightly controlled by automated systems to maintain stability and consistency across different production batches. One can notice how the mixing chambers rotate ceaselessly to prevent any streaks or inconsistencies in the pigment distribution. Transition to the next level occurs once the mixture is perfectly homogenized and ready for the high-pressure thermal phase. The prepared material now sits ready in the hoppers, prepared to take its final geometric form. This concludes the initial preparation phase, opening the road to the complex shaping of the individual components. 440 to 590 degrees Fahrenheit is the thermal range required to transform solid plastic into a workable molten state. Why is such a high temperature necessary for these small components? A standard heating process would leave the material too viscous to flow into intricate shapes. But at this specific thermal level, the mixture achieves a consistency similar to toothpaste. This allows the liquid plastic to be driven under extreme pressure, reaching 29,000 pounds per square inch into hardened steel molds. The molten material fills every microscopic void of the template. One can notice how the steel mold serves as the single master template, dictating the geometry of every brick with absolute finality. If a new shape is required, the entire multi-ton steel assembly must be replaced, as no deviation from the original design is permitted. But this is just the beginning. The material solidifies almost instantly upon contact with the cold internal surfaces of the mold. Within only a few seconds, the liquid locks into a rigid geometric form. The mold then opens in a synchronized mechanical motion, releasing the newly formed bricks in a steady, controlled rhythm. It is visible how the components emerge, like continuous prints from a high-precision press, moving immediately toward the primary inspection station. Why must every single piece undergo high-resolution optical scanning? At first glance, the bricks appear identical, but the sensors check for flatness and the precision of connecting features from every possible angle. Any piece exhibiting a faint surface scratch or a misalignment of even a fraction of a millimeter is discarded. These rejected elements are not wasted. They are collected and ground down to be recycled directly within the facility. The process is only gaining momentum. Automated guided vehicles, known as AGV robots, have navigated these factory floors since 1987. These machines move autonomously along predefined routes, approaching injection molding stations to swap full containers for empty ones. Each bin carries a unique barcode, allowing a central computer to track the exact quantity and type of elements in real time. It only looks obvious that all parts move forward, but the factory operates as a closed loop. Components that fail the optical test are fed back into the production line as reusable raw material. This preserves the purity of the plastic across multiple cycles while minimizing environmental waste. Only the perfect specimens proceed to the decoration line, where the characters begin to receive their distinct physical identities. Everything only gets more complicated at the printing stage. Facial expressions and intricate logos are applied using ultra-precise typography rather than manual painting or decals. A soft rubber pad descends to pick up ink from an etched plate before pressing it onto the plastic surface. To ensure absolute consistency, robots rotate each head and torso beneath the printing head, with timing synchronized to thousandths of a second. One can notice how inspection cameras monitor the ink application. If a line is misaligned by as little as 4/1000ths of an inch, the system triggers a rejection. Following the print, automated manipulators fit arms into shoulder joints and mount heads onto necks. The components then move to a storage and sorting zone where they are gently agitated in containers to optimize space before being sealed. The warehouse racks rise to a height of 121 feet. Automated counting systems weigh and measure every individual piece to confirm that the correct configuration is ready for bagging. This tightly integrated rhythm ensures that a brick produced today will fit perfectly with one manufactured several decades ago. Once the bags are filled, they are combined with instruction manuals and larger structural elements in a programmed sequence. 50,000 boxes are completed every 24 hours on the fastest production lines. Automated systems erect the cardboard structures, load the components, and perform a final verification before the lids are sealed. The camera glides along the conveyor as the boxes are marked with identification codes that link them to a specific production batch. At this point, the sets are locked in both physical structure and digital data. The transformation moves to the final logistics phase. Automated systems group the finished products based on their outbound destinations and pack them into impact-resistant shipping cartons. These are stacked onto wooden pallets and wrapped in multiple layers of protective shrink film by specialized machinery. From this central point, shipments are dispatched via trucks or ocean containers to major logistics hubs across the globe. A network of satellite distribution centers manages the final delivery to online warehouses and thousands of retail outlets. Through this coordinated supply chain, the product reaches more than 140 countries. While the resulting object is a toy, the underlying production system is an environment of remarkable industrial precision. The material leaves the factory, transitioning into a calm stage of global distribution. 150 years is the age some of the oldest managed trees can reach before they are selected for the pencil industry. The journey of a pencil does not originate within the sterile walls of a factory, but rather deep within the silence of the forest. Wood serves as the structural backbone of the entire instrument. To ensure maximum stability, ease of workability, and a clean finished aesthetic, leading manufacturers prioritize softwoods with straight grains that resist the natural tendency to warp and are easy to cut with precision blades. Why is the California incense cedar specifically chosen as the most prized raw material? At first glance, many wood types might seem interchangeable for a simple barrel. But without this specific cedar, the pencil would likely crack during the drying process or fail to hold its shape over time. It possesses a distinct natural aroma and a unique resistance to physical stress that others lack. These logs are never harvested at random from wild growth. They are sourced exclusively from carefully managed tree farms, where a strict cycle of replacement is maintained. For every tree removed, a new sapling is planted to ensure a sustainable supply chain remains intact. The process is only gaining momentum. Once harvested, the massive logs are cross-cut into uniform lengths and loaded onto specialized heavy-duty trucks bound for the sawmill. One can notice the equipment gradually lifting the timber as each rough, ordinary block of wood takes its first calculated step toward becoming a refined writing tool. Once the cedar logs arrive at the factory gates, the raw material must be processed with near-perfect technical precision. The logs are fed into heavy-duty specialized saws that slice the wood into thin sheets known as slats. Each individual slat measures exactly 5 to 6 millimeters in thickness. This is precisely enough material to form exactly 1/2 of a pencil's wooden body. But not every piece makes the final cut. The slats are carefully inspected by both high-speed optical sensors and the trained eyes of technicians to detect any physical flaws. Warping, knots, surface cracks, or any minute irregularity that might compromise the structural integrity of the final product leads to immediate rejection. The slats that pass this rigorous inspection move directly to the grooving stage. Each piece of cedar is guided through a high-precision milling machine that carves a series of shallow, parallel channels along its entire length. These channels are designed to cradle the pencil core, and their placement must be geographically exact within the wood. It seems like a simple mechanical task, but in reality, a groove that is even slightly off-center could cause the core to break during sharpening or shatter under pressure during use. To finish this phase, a thin coating of specialized oil or wax is applied to the surface of the wood. This layer protects the cedar from environmental moisture while giving it a smooth texture that makes the subsequent stages of assembly cleaner and more precise. 100% purity is the goal when preparing the sole of the pencil, which is the graphite core. Graphite is a crystalline form of carbon composed of layered structures that allow it to glide smoothly across paper. It is often mistakenly referred to as lead, though no actual lead is used in the process. This unique mineral is primarily extracted from deep, open-pit mines located in countries such as China, Brazil, Mozambique, and India. When a natural vein of high-quality graphite is discovered, heavy machinery or controlled blasting with millisecond delays is used to break the mineral away from the surrounding rock layers. Trucks haul the raw ore to a processing facility where it undergoes primary crushing and multiple stages of chemical and mechanical refinement. The objective is to remove all traces of soil, stone, and unwanted metals. One can notice how the equipment filters the material until it reaches a purity level of over 90%. The quality of this graphite, ranging from its inherent softness to the specific size of its particles, plays a crucial role in how the pencil feels in the hand. It determines how smoothly the tip writes and how durable the core remains over years of storage. Why must the purified graphite powder be blended with clay? The raw powder alone would be too brittle to maintain a solid shape. Clay acts as a vital structural binder that holds the carbon particles together. The specific ratio between the graphite and the clay defines the writing characteristics of every individual pencil grade. A higher concentration of clay results in a harder, lighter core, which is typically categorized as an H grade. Conversely, more graphite produces a softer, darker, and smoother stroke, which characterizes the B grade series. The mixture is kneaded thoroughly in large-scale industrial mixers until it reaches a perfectly even, homogeneous consistency. Next, the dense graphite clay paste is forced through an extrusion die into long, thin strands. These strands resemble dark spaghetti and are only a few millimeters in diameter. These delicate threads are then carefully air-dried to remove excess moisture before they are placed into high-temperature kilns. The temperature inside these furnaces ranges from 1,000 to 1,200 degrees Celsius. This intense heat treatment hardens the clay and locks the core's physical shape in place. Finally, each hardened core is dipped in a bath of oil or wax. This essential step reduces friction during writing. Transition to the next level. Alongside traditional graphite, factories also produce specialized colored pencil leads. Unlike standard cores, colored leads are composed primarily of vibrant pigments blended with wax, oil, and fillers, such as kaolin or talc. There is no single universal formula for these leads. It varies significantly depending on the specific product line and its intended professional use. For example, pencils designed for students prioritize softness and ease of application, utilizing a higher volume of wax for a blendable texture. In contrast, high-end artist-grade pencils demand greater color intensity and long-term light fastness. The mix for professional lines may include specialized resins or complex binders to ensure optimal performance on various paper types. Once the ingredients are blended into a uniform paste, the mixture is extruded into thin strands similar in shape to their graphite counterparts. However, it is visible how the process differs here, as colored leads are never fired in kilns. Exposing them to extreme heat would chemically degrade the pigments and alter the color quality. Instead, they are gently dried at lower temperatures to maintain their form, and then cut into standard length segments. 2 separate wooden slats are required to create the final sandwich structure of the pencil. On the production line, a slat that has been precisely grooved is placed onto a high-speed conveyor system. These grooves are positioned with technical accuracy, each one measured to a specific depth and spacing to perfectly fit the diameter of the core being inserted. The graphite or colored leads are then placed into each channel, either by automated mechanical arms or by hand. For premium or delicate lines, especially those with fragile cores, manual placement is often preferred to significantly reduce the risk of breakage. A second slat, carved with identical grooves, is then coated with a thin, even layer of industrial adhesive. It is carefully aligned and pressed onto the first slat, effectively locking the cores between the 2 wooden halves. This unit is then fed into a high-pressure press, where calibrated force ensures the glue spreads evenly into every fiber of the wood. Some modern facilities use heat pressing to accelerate the drying time and increase the bond strength of the adhesive. Even now, the solid block is not ready for the saws. It must rest for a set period to allow the adhesive to fully cure, ensuring the core remains precisely fixed at the geometric center of the wood. 17.5 centimeters is the standard length that each individual pencil must reach. The long sandwich block, with the cores sealed securely inside, is fed into an automated high-speed cutting system. Precision saws slice the block into individual sticks. These rough forms are then shaped using a profiling machine equipped with rapidly rotating blades. Depending on the design, the pencil body can be rounded, hexagonal, or triangular. Each specific form is chosen to affect how the tool rolls on a surface and how comfortably it rests against the fingers during long writing sessions. After the shaping process is complete, the pencils undergo another round of rigorous inspection. Both automated sensors and human inspectors weed out any units with cracks, chipped edges, or off-center cores. Only those that meet the exact engineering standards move forward. When the shape is fully defined, the pencils enter an automated painting line. Each one typically receives between 3 and 6 individual coats of finish. This begins with a base primer, followed by the main color, and concludes with an outer protective layer that guards against moisture and daily wear. While yellow remains a timeless symbol, modern manufacturers offer a wide spectrum of colors from deep burgundy to natural wood grains. The entire coating process is executed by industrial spray machines paired with heat-curing systems that ensure each layer dries quickly and adheres perfectly to the cedar. Once the paint is dry, the pencils move to the printing line. Every unit is gently rotated through a system of rollers or hot stamping machines that imprint the brand name, product code, and graphite grade. For premium models, sophisticated techniques like metallic foil embossing or silk screening are utilized to give the text a durable, polished finish. Some brands even offer personalized laser engraving for specialized orders. One small metal ring, known as a ferrule, is the final component added to many models. The assembly of the eraser is a symbolic step that transforms a simple stick of wood and graphite into an all-in-one tool. The erasers themselves are molded from a blend of synthetic rubber, softening agents, and mild abrasives. Automated machines press the rubber into the ferrule and then crimp the entire metal unit onto the end of the pencil. The pressure must be strong enough to secure the parts for years of use, but calibrated so it does not crack the seasoned wood. The step is inspected just as thoroughly as the initial milling of the slats. After full assembly, some models go through the final process of sharpening. The pencils are fed into a machine where a fixed blade carves the wood at a precisely calculated angle. The system adjusts the cutting depth based on the hardness of the core to ensure the graphite is exposed cleanly without any chipping. When the sharpening is complete, the pencils undergo a final round of quality control where they are checked for straightness, paint uniformity, and eraser stability. Only the pencils that pass every one of these standards move on to be sorted and packed into sets of 6, 12, or 24. Packaging is tailored to the product's market position, ranging from simple cardboard boxes to high-end tin cases or eco-friendly recycled materials. Once packed, the boxes are moved to distribution warehouses, ready to reach the hands of students, artists, and writers across the globe. The material is ready to move to the final phase of its journey without haste. 100% of the components in a standard pencil originate from globally dispersed sources, spanning from the cedar forests of California to the graphite mines located across Africa and Asia. Why is such a vast geographical range necessary for a seemingly basic writing instrument? It only looks obvious that any wood or carbon would suffice, but in reality, only specific geological and botanical properties ensure the tool does not break under pressure. The journey from raw material to finished product involves a transition from high-speed automated production lines to intricate manual adjustments. It seems simple to assemble wood and graphite, but the process is only gaining momentum as these elements converge. One can notice how the raw cedar is sliced into thin slats with millisecond precision, creating the housing for the core. Everything only gets more complicated when the human element is introduced to the assembly. While machines handle the bulk of the shaping and painting, delicate steps in quality control still rely entirely on the human touch to identify microscopic flaws. The equipment gradually moves the pencils through finishing stations where the surface is polished to a uniform smoothness. These incredible processes define the intersection of modern industrial manufacturing and timeless craftsmanship. The transformation from raw earth and timber into a functional object is now complete. The material reaches the standard ready for the final stage of distribution without haste.